This will be the lecture over chapter 19, where we'll study the kinetic theory of gases. See the learning objectives there. So the kinetic theory of gases relates the macroscopic properties of gases to the microscopic property of gas molecules. 1 mole of the substance is going to contain Avogadro's number of elementary units, or N sub A. Usually atoms or molecules, where N sub A is found experimentally to be 6.02 times 10 to the 23rd atoms or molecules per mole. The mass per mole, M, of a substance is related to the mass of an individual molecule of the substance by mass per mole is equal to the mass times the number of mass of the molecule times the Avogadro's number. Number of moles N contained in a sample of mass M sub SAM, or sample, consists of N molecules, consisting of N molecules, is related to the molar mass of the molecules and to Avogadro's number as given by the following. So number of moles is going to be the mass of the sample divided by the mass of that particular molecule, which we are the molar mass. And if we take the molar mass and we substitute it with M times Avogadro's number, we can get the same formula. So an ideal gas is one for which the pressure, the volume, and the temperature are all related by the ideal gas law, which is PV is equal to nRT. Here, the constant N is going to be the number of moles of the gas present, or N is not a constant, sorry. N is the number of moles of the gas present, R being the constant, 8.31 joules per mole times Kelvin, and that will be referred to as the gas constant. The second expression is going to be PV is equal to capital N, KT, where K is going to be the Boltzmann's constant. And remember, N here, if we go back, is going to be the number of molecules. So if we look, and I do want to make this point, as soon as I can find it, there we go. N is going to be the number of molecules, whereas little n is going to be the number of moles. So here we have a large steel tank that's being crushed by atmospheric pressure. Obviously, a pretty big example of the ideal gas law. In other words, pressure is going to continue to go up if the volume is taken down. And then eventually what you do is you end up crushing the entire container from the inside. So the work done by an ideal gas during an isothermal or a constant temperature change from an initial to a final volume is going to be given by this particular formula. So if we look here, we've got a PV diagram. What a PV diagram is you have a constant temperature, and along that constant temperature, you can see how the pressure varies with the volume. So at 320, that relationship of pressure and volume is going to lie along here. At 310, it'll lie along here, and at 300, it'll lie along here. This is also referred to as an isotherm, which means it has a constant temperature. The path shown along the middle isotherm represents an isothermal expansion of a gas from an initial state to a final state. The path from F to I along the isotherm would represent the reverse. In other words, an isothermal compression. Why is it a compression? Because, I mean, if you're going from here to here, you're watching the volume increase and the pressure go down. If you're going from here to here, you're adding pressure. So in terms of the speed of the gas molecules, the pressure exerted by n moles of an ideal gas is going to be given by this equation, where V sub RMS is equal to the square root of the velocity squared, or the average velocity squared, is the root mean squared of the molecules, and m is the molar mass and V is the volume. The RMS speed can be written in terms of temperature as this. So basically you can take a lot of these equations and rearrange them, and this is what you can come up with. So RMS is going to be a particular type of velocity of the molecule that we're talking about. We're going to be talking about several different, 3 different ones actually, and this is just one of them. So here are some RMS speeds at room temperature. We know what the molar mass of a lot of these compounds are, and then this is the root mean square velocity. The room temperature is going to be equal roughly to 300 Kelvin, roughly 27 degrees or 81 degrees, and that's pretty warm for a room, but it's convenient. So hey, what are you going to do? So if you were to get down into describing the energy of a particular molecule, you've got several different things to bear in mind here. There are several different degrees of freedom in which a molecule can vibrate or move, depending on its temperature. Now, if we're going to look at the average translational kinetic energy, in other words, moving in three dimensions, it's related to the temperature of the gas by 3/2 kT. And at a given temperature T, all ideal gas molecules, no matter what their mass, have the same average translational kinetic energy. When we measure the temperature of a gas, we're also measuring the average translational kinetic energy of its molecules. So let's say that you've got a gas mixture that consists of molecules of types 1, 2, and 3, where 1 is the most massive. This is the one in between, and molecule 3 has the least amount of mass. Rank the 3 types according to the average kinetic energy and the RMS speed. If we're to look at the average kinetic energy, we'll notice here there's absolutely no dependence on the mass. Because of that, all of these are going to have the same average kinetic energy. If we're looking at the RMS speed, however, let's go back to that particular formula. The RMS velocity is going to be equal to this expression, and you'll notice the mass is in the bottom. The greater the mass, the smaller the speed. So you will notice that since this has the smallest mass, this is going to have the greatest RMS speed, followed by this one, and then followed by that one. Now, mean free path. If you were wanting to find out what the mean free path of a gas molecule is, it's going to be the average path length between collisions, and it is given by that particular formula, where N divided by V is going to be the number of molecules per unit volume, and D is going to be the molecule diameter. If we look at our figure here, we've got something is coming in, boom, has a collision here, it can bounces over here, boom, has another collision, keeps going this way, boom, and so on and so forth, and just keeps colliding. So the question becomes, how long is that path on average before a collision is made? And that's where this formula comes in. So in that particular figure, you've got a molecule traveling through a gas, colliding with other gas molecules in the path. And although the other molecules are shown as stationary, they're also moving in a similar fashion. So we take that into account when this particular computation is made. So the Maxwell speed distribution P sub V, is a function such that P of V times dV is going to give you the fraction of molecules with speed in the interval dV at a certain speed. So this particular distribution is what gives you this particular form. Obviously, it's dependent on the mass, it's dependent on the temperature, and also the velocity. So you can see how that particular formula is charted with respect to speed here. Let's see if I can blow this up a little bit more. So depending on the speed, if you were to put in other values here for mass as well as temperature, you could create this graph. You end up with three different types of speed here. You've got your root mean square speed, you have your average speed, and then V sub P. So this is going to be discussed a little bit later here. But the average speed and the RMS, you've already been at least somewhat acquainted with. But the area of this particular part of the graph is going to give you the fraction of molecules with speeds within that particular interval. Obviously, this graph is going to change when you start varying the temperature. So you've got the average speed. You've got three measures of distributions of speeds among the molecules. You've got the average speed. You're going to have the most probable speed mode, if you will, and then you're going to have the root mean square speed, which is represented by this, which is the same formula as what we had before. Okay, molar specific heat at constant volume. So the internal energy of an ideal gas is a function of the gas temperature only. Does not depend on any other variable. So you got your internal energy here, and then you got 3/2 nRT. The molar specific heat of a gas at a constant volume is going to be Q is equal to N specific heat times change in temperature. The change in the internal energy of a confined ideal gas depends only on the change of the temperature, not on what type of process produces the change. So if you're going to take a look at this particular graph, you have an initial pressure, you have a final pressure, and you're seeing an increase here. It goes from one isotherm to the next, and you can see that this temperature increase is done without changing the volume. So it's an isovolumetric, as so you could say it. So the molar specific heat of a gas at constant pressure is going to be represented with this. And Cp can also be defined as the specific heat of the volume plus R constant. So for this particular checkpoint, the figure here shows 5 paths that are traversed by a gas on a PV diagram. Rank the paths according to the change in internal energy of the gas, greatest first. Obviously, if you go back and you want to take a look at the internal energy definition, the definition is this is going to be constant, particularly for all 5 of those scenarios, it's going to be the same. This is going to be the same. The biggest thing here, the greatest change that you're going to have is going to be a reflection of the change in temperature. The only thing that changes temperature more than anything else is going to be root 5. All of these other roots change from this temperature to this temperature. Therefore, all of those are going to have the same internal energy. So let's take a, a look here. So we've got a thermal reservoir down here. We've got insulation. We've got lead shot that's up here. And the temperature increase is done without changing the pressure. So if you look at the PV diagram, you're not changing the pressure, but you are in fact changing the volume. So the temperature of an ideal gas is raised from T to T plus delta T in a constant pressure process, as you see here. Heat is added and work is done in lifting that loaded piston. In other words, it's going to increase the volume. That's why the volume goes over. The process on a PV diagram is represented here, and the work, pressure times the change in volume, is given by the shaded area down here. So, if you're going to look at degrees of freedom for various molecules, and there are several things that go into this, all of them, as you will notice, monatomic, diatomic, polyatomic, all of these examples here, you have 3 degrees of freedom for translational motion. If you look at rotational motion, you're going to see that there's not any sense in having rotational motion or degree of freedom for monoatomic. However, for a diatomic, you'll have 2 ways to look at it in a rotation here for diatomic, and 3 for a polyatomic. If you add all of those together, you end up with a total number of degrees of freedom. And then therefore, your specific heat with respect to volume is going to change accordingly. And then the specific heat with regards to pressure will also change. So every kind of molecule has a certain number of degrees of freedom, which are independent ways in which the molecule can store energy. Each such degree of freedom has associated with it, on average, an energy of 1/2 kT per molecule, or let me say that again. Each degree of freedom is going to have an energy of 1/2 kT for that molecule, or 1/2 RT for the mole. CV over R versus temperature for a diatomic hydrogen gas. Doesn't look like, okay, this is the plot it's going to be referring to. Because rotational and oscillatory motions begin at certain energies, only translation is possible at very low temperatures. As the temperature increases, rotational motion can begin, and then when you get to higher temperatures than that, then you have oscillatory motion. Well, all of those different types of motions add to the degrees of freedom. And so our formulas here are going to change because of that. So you can start to see where rotational degrees of freedom start to enter in, at least at what specific temperature. And then as you go up to even further in temperature, then you start to see the oscillation. So depending on what kind of circumstance that you're in, you may have to account for that. So this is your monatomic, this is your diatomic, and this is your polyatomic type of molecule in regards to translation, rotation, and oscillation degrees of freedom. So when an ideal gas undergoes a slow adiabatic volume change, now adiabatic means there is no heat coming out or going in. That's why Q is going to be equal to 0. Then the pressure times the volume raised to some kind of constant, which we call gamma, and gamma is going to be equal to that. This value is going to end up being a constant, and it's the ratio of the molar specific heats for the gas. So the volume of an ideal gas is increased by removing mass from the piston. As you remove the mass, then you've got the gas is able to push a little bit further on that weight because it doesn't weigh as much. The process is considered to be adiabatic because you're not really adding heat or taking away heat from the system. So the process proceeds from I to F along an adiabat on the PV diagram. So if we look at our PV diagrams here, we have an adiabat as we slowly remove the shot, allowing the expansion. In other words, the gas can push and expand without having any heat transfer. So what happens with that? Well, let's say initially we start here and then finally we end up here. You can notice that we're going from one isotherm to the next. The pressure is decreasing, the volume is increasing. We're also noticing that the temperature is falling. And if you go back and if you look at the ideal gas law, that's what we would expect. So here's the summary of all of the major concepts that we're going to be encountering here. And I will see you in the next lecture.